Hi guys, you're welcome to this session. In this session, we are going to be looking at backpropagation. Backpropagation is a very important concept in machine learning, and that's what we are going to be looking at in this session. I've come to realize that a lot of people who explain backpropagation do not really give it the attention it deserves, because backpropagation is what enables us to be able to effectively use deep learning as we have it today, because this is exactly what updates the weights. This is what enables us to optimize our loss, to reduce our loss, and also enable us to, get a better model that is as close to the real life data as possible. To be able to model the representation. Back propagation is very important to that. And a lot of people have noticed I've not really paid a lot of attention to this. And I'm going to, for those who do, they just focus on the code and everything. But I think it's very important that we understand this from first principles, that we understand this from the actual concept of backpropagation itself. And that exactly is what I want to do today. Backpropagation. So what is backpropagation? I believe we all know that I believe most of the people who are going to be looking at this are people who are involved in data science and AI. So one thing that is very important is in deep learning. In deep learning, we have representation of data in a neural network. And how does that work? How that works is that we have some input layer here. We have some hidden layer in between, and then we have the output layer. So I'll say this is inputs, this is hidden, and this is outputs. Okay, so that's basically this. The input layer represents the data that is being fed into the network. The hidden layer represents where the computation happens, where the exchange of learning parameters happens. And the output layer is where we get the prediction by the model itself. Okay, where we get to compare and then we do a backprop. So, but what happens in this representation is, the sequential approach from the input down to the output, I'll say from the input down to the output is known as the forward pass. Forward pass. And what happens in this situation is we have our inputs, which are referred to as X. Okay, I refer to our input as X. Our input features, our input parameters, our input data. And when we are working with deep learning, we are talking about data here. So even if you're having images, or you're having audios, or you're having every other data forms, all of these data will be tokenized. All of these data will be represented in numbers, in data, in numbers that's, because these architectures can only work with numbers. So all of these formats will still be converted to numbers. And that exactly is what we are going to represent X as. X represents the input data, that we are having. Now, this input data, is being fed forward into the architecture. Okay, and what we are going to be having here is from this input, we'll be having Z1. So Z1 is supposed to be the transformation. Okay, the output of the transformation. The output of what? Is the output of W1 X plus B. Okay, W1 X plus B. So what is W? W is the weights, X is the input, and B is the bias. Okay, weights, X, and bias. So X is the input. So initially, when the model, if data is being passed into the neural network architecture, what we have here is random weights. No weight has been learned yet at this point. We have random weights being assigned to these input features. So that is exactly what we have, in the early layers of learning. And when we have this transformation at Z1, we call this linear transformation. Okay, we call this linear transformation. So this is linear transformation because the output gradient, the gradient is being computed, which is Z1. Okay, Z1 is being computed, Z1 equals W1 X plus B. So which is a linear transformation. Then after that, what we have is then the activation. Okay, we have the activation A, which is being applied. So the activation is the nonlinear transformation of the data. So oftentimes we do this to we apply this on each layers of our architecture. Of each layer, wherever, if you are familiar with deep learning, you know that for each layer of our transformation, we always have a nonlinear transformation, which is known as the activation function. And the activation function can come in different forms. It can come in form of ReLU. ReLU is often used in the hidden layers of deep neural network. And why is ReLU? Is because, so let's say A equals to ReLU of Z1. Don't forget Z1 is the output of the first linear transformation. So why ReLU? ReLU is known as rectified linear units. So why ReLU? Okay, ReLU helps us to smoothen out the non-positive values that we have in the transformation, because this is a lot of numbers, a lot of computation is happening. It's possible that we have some noise, so it helps to smoothen that. And how that happens is, let's take for example, we have this. We have the positive and negative axis over there. So what ReLU does is, at this point you have 0, so it picks 0 from here. And then when it gets to the positive, it shoots up here. Now, what happened is, whenever any number is being, passed into ReLU, if the number is negative, it's converted to 0. If it is positive, then it maintains it. So this helps us to smoothen out noises from the output of the linear transformation. So that is ReLU. And then the output of this, of ReLU, then we have the next layer. Okay, we have the next layer of the forward pass propagation. So here we have Z2. Z2 here is going to be equal to, don't forget we've computed Z1 earlier. So it's going to be equal to W2, W2A1. So this is A1, right? That's the activation of the first layer, plus B2. Right? So this is the transformation. So where do we get W2 and B2? So that's also random weights that is being assigned. So that's random weights being assigned. So don't forget I said that in the early layers or in the early periods of learning, no weight is being learned yet. All we have are just random weights. And then in our backward propagation, that is where we are going to start, evaluating the weight itself. We are going to start optimizing the weight. So these are still random weights. And at this point, what we have here is logits. Okay, so let me say this is a non-linear transform. Transform or activation. Okay, so here is logit. So when we talk about logit, we are talking about output probabilities. Okay, output probabilities, vector of output probabilities. So that is the logits that we are having here. So after the logit, what do we get is we calculate the loss. Okay, so you say L equals to loss of Z2, comma Y. So here Z2 is the logic, don't forget, and Y2 is the true output. So in this case, don't forget, you are trying to model a particular data to an output. So we are trying to model it. So by trying to model in a supervised machine learning scenario, you are going to be having the labeled output. And it is with this labeled output that we use to measure the loss. We used to, measure how far it is that our predicted output is from the actual output. So and that is how we evaluate our loss. And we have different scenarios of evaluating the loss. We have the mean squared error. We have every other, evaluation metrics too as well. So this is it for the forward pass. Okay, so this is it for the forward pass. Now, don't forget that we have some specific things here. A minute. Don't forget that we have some specific things here from the input X, to Z1, which is the output of the linear transformation, to the activation function, to Z2, and to L, which is the loss. So don't forget that, right? Now, we are now going to start looking at the backpropagation now. We are going to start looking at backpropagation. I think there's a particular mathematical concept that I'm supposed to introduce here, and that is the concept of the chain rule. Chain rule. Or before I go into chain rule, okay, so here is the output L. Now, before I go into chain rule, I think it's also important for us to talk about the backward. So this is the forward pass. Forward pass, right? So I think it's important for us to talk about the backward propagation, right? So how does backward propagation works? Okay. Backward propagation works in steps of, as opposed to moving from sequentially from the input down to the output, and measuring the loss. We are going to move backwardly, and that's why it's called backward, from the output to the input. That is from the loss down to the input here. So that is backward propagation. And what do we do there? What we do here is we tend to measure how each factor affects the other. Okay, how each factor, affects the other. So let's say, for example, we are going to be measuring minutes. So let's say, for example, we are going to be measuring the loss, how the weight, for example, affects the loss. Because in the initial time steps, we are just assigning random weights. Okay, so how do this weight affect the loss? So because it is this weight that helps to, that assign values to each of these input parameters to help determine which of them, is important in predicting the output. So this plays a very important role in predicting the output. So how do we then train our model to understand, what feature is assigned, higher weight to help, understand this particular representation to be able to model it to the exact output as close as possible. Okay, so and that is going to lead us to what I'm going to call the partial derivative of the loss, based on the weight. So you are going to be looking at how does the weight, the randomly assigned weight, affect the loss. So you're going to be looking at how the weight itself affects the loss. And for us to be able to do that, okay, we are going to say the LDW, equals, don't forget that our forward pass is x. So I'm going to call this W now. I'll say W equals W towards Z1, towards E, towards Z2, and towards L. Okay. Now, we want to see how the weights, affects the loss. So we say the L dW equals the L the Z2 times the Z2, sorry, the Z2, the A times the A, the Z1, okay, times the Z1, the W. Now we are going to come back to this formula very soon. For us to understand this very well, we are going to talk about chain rule. So chain rule is a mathematical concept that helps us to explain how we can model relationship between, a chain. We can model how a particular factor affects the other between a chain of interconnected events. Okay, so let's say, for example, if L is a function of X, that is, if loss is a function of X, okay, then we can say, according to chain rule, then we can say the L, the X equals the L, the G times the G, the X. If this cancels this, then we are left with the L, the X, which is what we have here. Okay? So which is what's going to get our thoughts into chain rule. And an example of how this works is to say, let's say, for example, we have G of X equals X squared. Okay? G of X equals X squared. So for us to be able to compute the G, the X, okay, this is what we are going, this is what we want to compute. For us to be able to compute this, the G dx is going to be equals to what? 2x. That's the first derivative of the function G of X. Now, we have another one that says L equals to G to the power of 3. So this is the first function, and this is the second, representation. This is the second equation. So L equals to G to the power 3. So to say the L, the G equals to 3G raised to the power of 2, right? Okay. So now we have this and we have this. So we know for us to be able to calculate the L dx, like I said, the L dx, so we have the L dg times the G dx. Okay. So now that we have this, then we can say the L dx equals to, don't forget the L dg, the G times the G dx. What is the L dg? This is the L dg, which is 3G squared. So we have 3G squared times the G dx. The G dx, this is it here, which is 2x. So we can now say the L dx equals to 3 times 2, 6, 6xg squared, right? So that is the L dx. But let's say if G equals to x squared, if G equals to x squared, then then we can now say the L, the x equals to 6x. Don't forget G equals to x squared, which is G of x equals x squared according to the function we had earlier. So you can now say G here is what? X squared. then squared. G itself is x squared. So don't forget the squared is still there. Then you can now say 6x, x to the power of 4, and that's going to be 6x to the power of 5. So, the L, the x equals to 6x to the power of 5. So this is how we can, model the relationship between two factors based on sequence of events or based on sequence of dependencies. Okay, so this is exactly how we are going to compute our back propagation. Now, some things are very important in this. Some things are very important in this. Don't forget I mentioned that in our forward pass, what we have is x or w in this case. I'll be using w. Say w, z1, activation a1, z2, which is the output logic, and then the loss. And then what we are trying to compute here is how does the weight itself affect the loss? So which is the L, the W, right? And I've mentioned the formula here. For us to be able to calculate that, we say the L, the W, that is how does the weight, the randomly assigned weight that is being assigned a forward pass, how does it affect the loss that we calculated on the output layer? So that is what we said. The LDW equals the L, the Z2 times the Z2, the A1 times the A1, the Z1 times the Z1, the W, right? Which is the formula I gave us, earlier. Okay. For us to be able to calculate this, so you have to look at what each of them represents. Okay, just a minute. Now, we have the Z2. Don't forget that when we talk about the L, that is how does the L the Z2 here, what this represents is the output layer. Because here we are looking at the gradients of how the output logic affects the loss. Okay. So here is outputs. That's how the output logic affects the loss. That's output gradients. The output gradients. On backward propagation. And then for the activation function, where we have the A1, the Z1. So this is where we applied ReLU. And don't forget that in this scenario, where we applied ReLU, like I said, ReLU smoothens out the noise or negative negative output of the linear transformation. So it filters it. And just keep, everything zero, anything negative is turn zero, and then keeps the positive value. So this, I'm going to say this is Z1 greater than 0. Okay, so this is Z1 greater than 0, right? Okay. So that is basically that. So we are going to look at each of them in greater depth. So like I said, they have the Z2, right? Don't forget that I said that is, okay, so this is known as the gradients at output. Let's say the output gradients. So this is known as the output gradients. And then also we have Z2 itself, which is what we said, was W2 A1 plus B2. Okay, and don't forget that I said this is the logit that is being calculated, after the nonlinear transformation. So to say, for this, we say the Z2, the A1, okay, we call this the transpose of the second weight. It's this transpose of the weight assigned on the second layer. Okay, so don't forget that the output of the first layer is delta 2. So here we call this the transpose of the weight on the second layer. And this is also, then we refer to this as D2 W2 transpose. So this is the transpose, the two transpose of the second layer. So because this is, we are adding the output of the first layer to the randomly assigned weights that we have here. Okay. And then this remains, then just add the transpose to it. So, which is why I say like delta 2 W2 transpose, right? And then for the third layer, which is, we said A1 equals to ReLU or Z1, that is basically max 0, 0. That is the maximum between 0 and 0 and Z1. Of course, 0 is filtered out, I mean the positive values. So if Z1 is greater than 0, then it remains. If Z1 is less than 0, then 0 remains. That's max, right? And we can also take the derivative of that by saying the A, the Z1, is equals to 0, 1, 0 if Z1 is less than 0, and 1 if Z1 is greater than 0. That's the derivative of that. I will call this the indicative function. I believe it simply is easily understood from the graph that we have from ReLU, right? So we have just this. Okay. I believe that is easy to understand from that point there. And then for the last one that we have here, which is okay, so that's basically that. So since we've talked about the output transformation, which is the output signal or gradient at the output layer. So I think that is all about that. Then we can now say the L, the W, equals the L is Z2, which is the gradient at the output layer, times W2 transpose, okay, times the ReLU, which is 1 for where Z1 is greater than 0, and X transpose, right? So that is basically that. So to mirror this, we can mirror this with, let's say, the L, W, equals to the L, Z2 dot, what do we have there? The Z2, the A, dot, so which is this, the Z2, the A, dot the A, the Z1, dot, which is this, the Z1, DW, which is this, right? So that is basically how we've been able to represent that. Okay. And then the output error, is being measured here. So that's that about the output gradient. Okay. Uh, Just a minute. So we've talked about loss. We've talked about loss. So for us to be able to truly measure the loss itself, we have different performance metrics being used to evaluate the loss. So to evaluate this loss itself, because the loss will be computed at the output layer. So we have different, loss functions that are being used, which helps us to, compute each gradient piece. Okay. So let's say, for example, we have delta 2 equals to dl is it 2, right? Which is what we have here at the output gradient, right? Now, so this is the gradient with respect to the output logic. I've talked about that, and that's the starting point of the backprop. I've talked about that as well. So for MSC, for mean squared error, I don't know if I've explained mean squared error. Let me do that. So for mean squared error, the loss itself is 1 over n times the summation of y minus y prime squared, right? Y prime, sorry, I made a mistake there. Okay, y prime minus yi. So yi is the output is the output feature itself, the output from the real data. While y prime is the predicted output. So what we just do is just we take a mean average, between the output. So we just subtract the output, predicted output from the true output. We take a mean of that, and then we square it. We square it for negative values. We square it for negative values, and then we take an average of that to be able to have an understanding of what the average of what the mean square error is. That's basically the mean squared error. Now, if I'm going to be taking a derivative of this, don't forget this is summation y prime minus yi squared over n. That's the loss, right? Okay, to take a derivative of this, you can say the L dz. Okay, don't forget that this is the output, the output logics where we are trying to look at how the output logic itself affects the loss. So here the LDZ here is going to give us, so the first derivative of this, so you're going to be having 2n, okay, 2 over n, sorry. Because this itself is going to be 1 over n. 1 over n. Then we have 2 into z minus y. Okay, so at the end of the day, we have 2 over n into z minus 1. So that is the first derivative of that. That's what it gives us. Okay, so someone might want to ask, how does this y predicted change to z? Don't forget that we are talking about z is the predicted, is the output logic. You know, we talked about that here. I mean, where did we talk about that? Yeah, so z is the output logic, right? This is it. Is the output logic. So whenever you are talking about the output prediction, it's still the same thing as z. So that's the reason why we said, you know, the partial derivative of dl dz equals to 2 over n z2 minus y, which is the output logic. So that's basically that. Okay. So what we've done here is just simple. Okay, we have x, giving us z1 equals to w1x plus v1, right? Then we move up onto the next layer, which is a1, which is red, z1, and then z2 equals to w2 a1 plus b2, right? That gives us, and then we have the loss, right? The loss. So this is forward pass. And then when we do when we compute the gradients, we do the partial derivatives across from forward down to, from the output down to the input. That is where, we compute our backward propagation. Okay, so that's basically that. And then don't forget, this is going to change. This particular one is going to, so this is computed for MSc. That means squared error. This is going to change if you are going to be talking about softmax, for example, or we'll be talking about different other, you know, uh, loss functions. It will be different. So that is basically that. To look at the backward pass carefully again, so we have the loss, and then we have E2 equals to the L, the Z2, right? Then we have uh, the L, the W2, okay, right, which was the two W2 W transpose. Then we have the L, uh, the B2, which is theta 2, right? So here is computing gradients for W2, and here is computing gradients, here is for B2. I think another question that you may also want to ask is, I mean, why are we using ReLU? Okay. So another question you may want to ask is, in our activation function here, we used ReLU. So someone may want to ask, why ReLU? Why are we using ReLU? You realize that what we are doing are partial derivatives. There's a partial derivative that is reducing, the value of the value, itself, the value gotten across the forward pass. So imagine what we'll be having if you're having negative values. Imagine how small the number is going to be if it is negative value. So it's going to be smaller. So just imagine what it will look like when we are in our third iteration of backward propagation. If you're having a third layer and we are doing a backward propagation, the value is going to be smaller, right? So we don't want negative value because that's going to lead to vanishing gradient. Vanishing gradient is when the gradient becomes so small that very little is being added to the weight. Okay? And that's exactly what we are going to be having if we are computing negative gradients or we are computing negative weights. We're having negative weight updates. So we don't want negative weight updates. If we are having a negative, we want it to be 0. If we're having positive, it should remain. The moment we start computing negative values, then we will be having very smaller values to update the weight of the model itself. So I don't want that. It's going to lead to vanishing gradients, vanishing gradients. So, and that's the reason why ReLU helps us to handle that. It helps us to filter the negative noise and then keeps up with the positive values. Okay. So here is where we are going to be stopping on the mathematical intuition. In our next session, we are going to code the implementation of gradients of backward propagation, and we'll see how that works. Hi, we are going to go on the coding session now to implement backpropagation. So I'll be sharing my screen now. Okay. Yeah, so you're going to be implementing backpropagation. Like we've all known, we are going to import, the required libraries. So what you're going to be doing here is basically to see how, how we can implement backpropagation in pure Python, and then we are going to visualize that, in graphical form. Okay, the first thing to do is to import required libraries. Right, so first import NumPy. Okay, then the next thing is to import plotly pyplots as PLT. So the first thing we are going to do is the next thing we are going to do is to assign so you are going to assign variables. Assign variables. So what that means is, for example, things like weight. We talked about weight while we are proving, backpropagation. We realize that weight initially are randomly assigned values. So that will be, assigned as well. We're not going to be training this on, normal data, but we are going to, add X feature as well to be able to, showcase how this backpropagation works. Then we're also going to be assigning, while true, which is the labeled while outputs labeled on our data sets. And also we are going to assign learning rates and gradient steps as well. So something is also very important for me to explain on these concepts before we proceed. Okay. So this was the note we used in our last session, to explain backpropagation. So one thing I am going to also explain, since you are going to be talking about uh, learning rates and steps, is to talk about the effect of backpropagation itself. So at the end of the day, we are going to be wanting to minimize error. We are going to want to model. We are going to be training the model to be as close to the original data set as possible. I mean, that's the reason why we are minimizing, looking at how the weight, affects how the weight affects the loss. And also that's the reason why we are trying to, evaluate the performance of the output prediction, using those evaluation metrics, mean square error, and so on. But on another level, one thing we are also going to be using to monitor the performance of our model is we are going to be using something I call the I mean we are going to be using something I call the graded descent, to also evaluate this. And this can be well represented, using learning rates and number of steps. So I'm going to be showing a particular graph here. Okay, I'm going to be showing a particular visualization here. So at this point, let me clean this up. Okay, so at this point, we call this the global minima. Okay, so this is the point where we want our model to be able to reach. Okay, this will be the minimum where we want our model to, to be able to reach. And for us to be able to do that, we are going to be using our learning rate. So our learning rate is how, fast the model, how fast the model is to approach the global minima. Oftentimes, we want our learning rate, LR, okay, we want our learning rate to be as small as possible to ensure that, while it's taking this number of steps, okay, it is small enough to ensure that, we are seeing that observable change as it approaches the global minima. Because if it is large enough, it can just offshoot the global minima and then, increases again. So we want to ensure that the learning rate is as small as possible to be able to consistently approach the global minima. So let's say, for example, if we have 0.1 step, at each time steps, and then it offshoots the global minima at some point, that could be considered large. And if that is observed, one thing we want to do is to reduce the learning rate to something like 0.01, so that no matter how small, it takes, it eventually approaches or reaches the global minima at some point and does not just offshoot it. So we are going to define those variables here as well. I just have to explain the concept of the learning rate and the steps and, approaching the global minimum. Okay, so we are going to assign this variable. So initially we are going to be having W to be 0.0. So don't forget that I said the weights are randomly assigned values. So the next is the bias itself. The bias is also length. So here we are also going to be having 0.0. Then also we'll be having X, which is the length feature. So this is going to be 1.5. So these are just random values. And then also we are going to be having Y true, which is the predicted out, which is the actual output. So Y true is going to be 0.1. Then also we are going to be having LR, learning rates, with 0.1 as well. And then also we are going to be having steps, that's the number of steps it takes to reach the global minima. So we are going to be taking 30, for example. Now, after this defining all of this, The next thing we are going to we are going to be defining are some very important functions. The first function is going to be the forward function. Okay, so this forward function is the one that helps us to predict, takes our input feature, the weight and the bias to make prediction on the output label, right? So that's basically it. And I'm going to be going back and forth in explaining to ensure that we get the deep mathematical intuition behind this. Okay, so on that, I'm going to explain something else as well. So on this, if you look at a simple, two-dimensional graph where you have, your y and your x-axis, right? So in this line, in this graph, so let's say we have, a straight line right here. So this straight line, forming a right angle triangle, right? So at the end of the day, we'll be having, the y denoted, on this y-axis. That's the change in y. And then here as well, you have the change in x, from 0 to x, from 0 to y as well is the change in y. And then through this, we'll be able to measure our gradient. So to measure our gradient, we say gradient n equals to change in x. Oh, sorry, change in y. Change in y, whereby change in x. M equals to change in y over change in x. To get our y, which is this, which is in this case is going to be our output prediction, we can say y equals to mx. Okay, y equals to mx. So this is a simple straight line equation, the equation of a straight. So this is referred to as the equation of straight line. Okay, y equals to mx is referred to as the equation of straight line. So to get this perfectly, so we could also measure the intercepts. The intercept is the line between is the distance between where this line crosses the y-axis and the origin. So we can say y equals to mx plus c. So that's c is the intercept. But in machine learning, we consider this to say y equals to wx plus b. Why? Because this is going to be the line, this is going to be the equation that will be used in linear regression. And in linear regression, we are assuming that there is the features, right? The relationship between the feature and the target is linear. We are assuming that there's a linear relationship between the features and the target. So when we have such kind of relationship, we often use linear regression. And that is exactly what we are going to be replicating here in this particular task. Okay, so let's get back to code. Okay, so we are going to define forward where we are going to be, implementing, the function, the equation of a straight line to be able to get our output prediction. And then also we are going to define loss to be able to evaluate our output prediction. And then also we are going to define backward. So it's this backward that we implement the backward propagation. So for forward, we define the function. So inside of this, we have our weights, our bias, and our input feature X. Okay, so here we have our y pred equals to W times X plus B, right? And then after computing the y prediction, they will return y, y pred. So that's the first function we are defining. So the next function is the loss. So here we have the y pred and the y true. So loss is to evaluate, the performance of the model. I mean, how far is it from how far is the prediction from the actual value, from the ground truth? So in doing this, you'll be implementing mean square error. Okay. So here we are just going to be returning. We'll be returning, sorry, we are not implementing the square error. We are just returning the square of the difference between the actual and the predicted. So why? Because we want to filter out negative values. So we have y pred minus y true. And, we raise that to the power of 2. So yes, square that. Now the next thing is we define backward propagation. So inside of this, we have the weights, we have the bias, we have the x, we have the y true, and the y pred. Don't forget that all of these are very important, in proving backpropagation, in seeing backpropagation in mathematical form. So when we're able to see how the weights basically, affect the loss, because at the end of the day, we want to minimize loss. That's the essence of backpropagation, to minimize loss. That's it. So to be able to do that, you do that by modeling, by trying to understand how the weight affects the loss, right? And then since the loss, the weight itself is randomly assigned initially, then that is also done by chain of interconnected dependencies. Okay, it's not just weight and loss. There are also other interconnected dependencies that affect the weight, which then affect the loss. So, and we'll be able to see that in our last section on chain rule. So in this case, for example, so here we are going to be having DL. We had DL DZ2. We said in our last session, we said DL DW, right? Is how weight affects us equals DL DZ2. DZ2, don't forget, I said is the output logic, which is the proper distribution of the prediction. So that is also known as Y pred. So just in case. So here we are going to be having DL the y pred. Okay, where the y pred equals you have 2 times. So now y pred is this. Okay, so we are differentiating L. So this is the loss. Now don't forget that L okay, L equals this. I hope you don't forget that. This is our L, this is our loss. So if we are differentiating L with respect to y pred, then that means we are going to be having 2 y minus y pred. 2 times minus y minus y pred. That's just basic differentiation. So that is basically that. 2 times this y minus y pred. Now, then the next thing we are also going to do after getting this is to look at the L, the W. So this is going to be the L, the y pred times X. Don't forget we talked about this in our last coding session, where we're able to say the next derivative after that is going to be del dy pred, which is del the logit, del dz2 times x, or which I call the sigma 2 times x, or w transpose. So it's still the same thing. Okay. Then the next thing we have here is the L dB. So here the L dB, say it is the L dy pred times 1. Okay, that is that. Right? So at the end of the day, what we return on the L dy pred, sorry, the L the W and the LDB. W and the LDB, right? This is, so these are the three functions we need. Now we want to train. We want to train this model. Now to be able to train, the first thing we need to do is we will need to get, to have a list of some values which we are going to. So some values are going to be appended into this empty list, which we are then going to use to observe, the back propagation in visualization form. So I'm just going to, put those variables here. So here, for example, we have W east, B east, loss east, history. So east is for history. Okay. So this is going to be small W. So don't forget that. So in our W history, which is our weight history, don't forget I said initially it's randomly assigned weight, and you can see the initial weight 0.0, there. Then same thing as the bias as well. They're also randomly assigned, so you can see 0.0 also here. So the loss history, loss are also going to be evaluated over time, based on the number of epoch you're able to get. You're going to, observe the loss over time to see the performance of the model. So that will also be assigned here. Also, the prediction history will be here, DW, DB. So since you're also going to be minimizing the weight and bias, to ensure that we get as close as possible to the output prediction, we model, we try to fine-tune weights and bias to ensure that our true value corresponds to is as close as possible to what the model is predicting. So that will also be tracked here as well. So the first thing we are going to do is we are going to use a for loop to do that. So we have something like for step in range, steps. Yeah, steps. So within this for loop, the first thing we are going to get, the first thing is the output prediction. So we have our white red. Okay. Oh, so you can see how interesting this thing is. The output prediction is the first thing we are going to get. And don't forget in the forward, we have W, which is our weight. We have what else again? B, which is our bias. And then we have X, okay, which is the feature itself. So here we get the output prediction. Then the next thing is the loss. Interesting. So loss, what do we pass into loss? Y prediction, which is what we got earlier. Y prediction and Y true. So the Y true is what we've assigned up here. Look at the Y true here, 0.1. So that's what we've assigned there. So that's the output prediction and loss. Then the next thing is our back propagation. Very interesting. Next thing is back propagation. So since we have a function that computes that, so we are just going to store the output of that in a predefined variable. So here we have the held DW, the held DW, and then so don't forget, I mean, just what we have here. Okay, so here we have DLDB equals backward of what do we have here? Our weights, right? W B, supposed to be small W, and B, then what else? X, then what else? Y true, then what else? Y pred. So yes, that's back propagation, right? Then after that, we append them as needed. So we append, each of them. So for example, Y pred prediction is being appended its prediction history, loss history, the LDB, being appended. Sorry, so here we have WW, and then the B. So that is gradients. So that's gradient update for the weight and bias. Sorry. So the W. So this is exactly the essence of backpropagation. What we want to see in backpropagation is to see the gradient updates within the weight and the bias. Because if you look at the equation of a straight line, the only thing, so this is the equation of a straight line. The only thing that is going to ensure us to be able to have something, the only thing that models the output prediction is the weight and the bias. The x itself is a static value. Nothing can be done about the input feature. But what can be tweaked is the weight and the bias to ensure that the output prediction is as close as possible. So which is exactly what the model needs to learn. So in this case now, what we need in backpropagation is ensure we're able to get a gradient update for the weight and the bias, full stop. So in that essence, I'm going to be, appending some values, some of these, values there. So I'm going to call this loss. So loss, what do you call it now? Loss is dot append loss, right? What else? Prediction history dot append, what's that? Y true. Sorry, widespread. That's widespread. Prediction history. It's appending widespread. Sure. Then the next thing is DW East. That's gradient update on the weight. DW East dot append DW, and then DB East dot append DB. So that is that. Now the next thing I want to do now is so after reaching a certain point within the epoch, so you say, for example, if step is less than 8, okay, or step is same as steps, okay, or step is same as step. Don't forget that that step increases. Now it's same as step minus 1. So don't forget this is starting from 1. So steps, the length is starting from 0. Sorry, not from 1. It's starting from 0. So the length of the steps itself is going to stop at steps minus 1. So that's why we have that. So now the next thing is, if you have this, then okay, no, let's just abandon this. Let's just leave this. We don't need this. Okay. So now the next thing we need to now do is, update the weight itself. So you're not going to update the weights. And how do we achieve that? Say W equals W minus LR times dW. Okay. So this is we trying to approach the global minimum based on the gradient update. So the new weight equals to the old weight minus. So don't forget that the weights. Oh, I'm not sure if so we had this bell curve shape where we are trying to reduce, descent across the weight based on the learning rate. Okay, and the gradient update. So it's the gradient update that informs how much we descend to the global minimum. So that's basically that, and then you can see that the multiplicative property of this. The higher this, the higher the gradient, the higher the weight. So that's going to and that's the reason why whenever it is that we are randomly initializing our weight in deep learning, it starts with very small value. So the reason why it's going to start with very small value is the moment you start updating the weights through backpropagation, like you can see here. If the weights are too big, it's going to lead to very big gradients, and that is exploding gradient problem. Okay, that's going to lead to a problem in machine learning that we call the exploding gradient, where the gradients are too big. Okay, it leads to very big gradient updates, and that confuses the model. It confuses the model. So we want to ensure that whenever you are randomly assigning your weights as small as possible to ensure that when you are doing your backpropagation, very small, steps are taken to reach a global minimum. So that's what we have here. Then the next thing we have is the bias. B is also going to be calculated B minus LR times dB. So we have that as well. So what we do here is, so then we append this. So you say W east dot append W and B east dot append B. Yeah. So that's basically that. Okay. So that's basically that. Okay, so that's that. Now since we have gotten this, the next thing we are going to do now is we are going to be plotting some specific graphs. Okay, but before we do that, we are going to set in some certain figures. Let's say visualization. Before we go there, I just want to run this. Let's see, we can run this and see some of our values. Some of the values stored in W east and B east and loss east. So we're going to just print this. Print what do you call it? With updates history. So say W east. Then you also have bias update history as well. Bias update history, which we will call the B east. Then okay, no. So I was looking at why we had red. So loss history as well. So I'll say loss history. So loss east, right? So basically that's what we need. Oh. Yeah. So that's basically what we need. So let's try to run this and see what we have from there. So say Python gbs.py. I'm not sure this is going to run, but let's try it. Yeah. This is not callable. This is not callable from loss. Loss lists. Loss function. Okay, so that's the function loss. Yes, y true. Script. Loss, okay. Oh, sorry. So I made a mistake here. So this is not supposed to be this is not supposed to be loss. So this is supposed to be loss val. So what happened here is I was calling the function and I was assigning it to the function. And that's the reason why it's telling me that float is not callable. So I cannot call the function. So that's what it's telling me there. So this loss val. So this is supposed to be loss val. Yeah. So basically that. So let's see this. Oh, great. So you can see, so it might look like nonsense, but yes, these are the values of the weight update. So you can see very beautifully from 0, we're able to have all of these amazing gradient updates. Same thing with the bias, same thing with the loss. And one thing I think is interesting about the loss is, so you see the loss, started small, then, it became significantly big. So it started large, right? 0.1, 0.1, up until exponent minus 29. That's significantly small, right? Again, very, very significantly more. And that's very, very, very beautiful. Okay, so you can see how we're able to minimize the weight, the loss. Very, very, very interesting, in a very interesting way. So that's amazing. That's really amazing. The next thing that'll make all of this to make all of this to make sense is I'm thinking of just plotting the loss. Okay, I'm thinking of just plotting the loss, So I'll say PLT dot figure. So I'm going to first set the graph size. So say fixed size. Fixed size is 8,5. So let's use 8,5. Now the next thing I want to do here is PLT dot plots. Don't forget that the step. So each of these steps is like the epoch. Okay. So in each epoch we get the prediction, the loss, the gradient, the what do you call it? The derivative on B and on weight and bias, the loss, so we append the loss as well, the prediction, the DW and these, then we compute the weight of gradient updates, right? All of that. So what I'm trying to say is in each of these steps, we're able to compute each of these. And then over time it's reduced. You can see how significantly each of these loss reduces. So which we are going to see here. So here we are going to have range of steps. So it's true range that we can be able to have our epoch on the x-axis, right? And then we have the loss east on the y-axis. Okay. And then the next thing is PLT dot x label. On the x-axis, what do we have? We have the epoch or step. The PLT dot y label. On the y-axis, what do we have? We have the loss. Okay. And then we have title. So you can say loss over I want to show grid. So let's okay. Anyway, let's just say PLT dot show. Let's see if grid is necessary in the future. Show it. So here we are going to run this again. Oh, okay. So you can see how significantly the loss reduced its time. I don't know if you are seeing this. If you are not seeing this, let me share the screen again for you to see. Okay, so what you are seeing here is the visualization of how the loss, reduce over time. This proved that backpropagation works, and it is through backpropagation that we can see the loss effectively, reducing. In fact, over the first, I think, second epoch, this is probably the first, this is probably the second and third, or the third epoch already, we've reached the least, we've reached a very significantly lower loss. So that's how interesting backpropagation is in deep learning. Very beautiful, right? That is that. Now you're going to try to, visualize some other, do some other visualization. So I'm trying to do something. I'm trying to plot all of these things on a single grid, which I think will make more sense. So let me just plot all of this on a single grid. I'll plot all of the graphs on a single grid, so it's going to be much more easier for us to see. Okay. So let's plot the graph. Great. So I'm going to show this here. Right, so here we can see this very interesting graph, right? Very interesting graph. So you can see the loss over time, which I've shown you earlier, the weight over step. So you can see how the weight increased. I mean, we started from 0, randomly initializing our weight. So up until what we got here, right? And then also we're able to get our bias as well significantly increased from 0. You can see that. And then this prediction versus truth table. So over the first, second few epoch, we had, first, second, third epoch, there was some, improvement. But as soon as it reaches the fifth epoch, right? Most especially this fifth epoch, you can see. So the prediction, meets the true value. So if you look at our code earlier, you realize that the true value was what? Was 0.1, right? The true value was 0.1. And, we met that on the fifth epoch. So that's the beauty, right, of backpropagation. I'm very certain that by, following through with this session, you have been able to truly understand, how backpropagation works. If that's true, hit the like button and subscribe to this channel. Thank you, everyone. Bye for now.